I'm Matt Cavanagh. Ruined my intro. But yeah, I made a game called Vicious Attack Llama Apocalypse. It's the world's best mass llama slaughter roguelike, lightish, couch co-op, top-down twin-stick shooter. I'm now working on a game called Backdoor Invaders, and no, no, it's not a joke. It's like a heist game where you contract aides. No, like you contract, like you pay accomplices, like people that help you. And it's kind of like Ocean's 11, and you plan out heists. So, yeah, I really just come to these conferences to get the free food, because game dev is game dev, but I hope you enjoy it. So, the goals here was to make a fully automated catapult. So, pressing stuff is cool, but like having something with a magazine that can continually fire for no reason at all is also really cool. I wanted as much as possible of it to be 3D printed because I have a lot of 3D printers. So like, if I can justify them by this stuff, then yeah, makes my wife happier. And then finally, I wanted to see if you could accurately use computer-based physics simulations to predict what would happen in the real life. So like optimize something by using a computer instead of spending hundreds of hours doing it in real life. So now 3D printing. Who has a 3D printer here? Cool, like 3 of you. 3D printing, it used to be very expensive. My first 3D printer was, hello mouse. My first 3D printer was this piece of crap over here, and it was in about 2012. You had to spend a weekend building it. It printed terribly. It did everything terribly. But now we're in 2019, and you get a printer like the Ender 3 for like $4,000. And it prints beautiful things. So 3D printing has really come a long way, and you can do a lot with it. You can design and print stuff at home. Like if you look in this picture, this is in my room. That little red thing over there is a super low profile bracket that I made to hold up those shelves. I didn't want those ugly metal ones that you get from Builders Express or whatever. So I designed one, and then you can use programs like Fusion 360 that I'll show you just now to do stress analysis to see where this thing is actually going to break. And I was still a bit worried that something like this big, made out of plastic, whether it would actually hold up expensive stuff. So I put the brackets like on a wall, put a plank there, and I pushed the plank until it broke, but the plank broke first. So that worked out, and then also in that picture, I've got like some purple shelves at the bottom. And you can also see I've got a few 3D printers. I started with the one, and then the wife was like, okay, this is all. And then we got 2, and she was like, okay, but for real. Now I have 8, and the rule has changed to like, everything has to stay in that room. So I'm going to show you some 3D prints quickly. So I don't know how much you guys know about 3D printing, but you don't have to just print normal plastic anymore. You get a whole bunch of composite materials. So this over here is Man of Steel, like Superman, printed out of a filament called E-steel. So it's actually got metal in it. You still get really good quality, it's super smooth, and it's got steel, which is kind of cool. And this was printed on a 4,000 Rand printer. Then this is a llama from my game. I really did make a llama game and spent 3 years of my life on it for some reason. So this is printed out of wood. It's about 40% wood filings inside plastic. It gives it a really cool like wood texture. You can use wood stainers and stuff on it as well. This over here, that's a flashing light. This is some software I'm working on, so you can just like drag colors over an object. So here I drag purple at the top, blue at the bottom, and then white on the like other bits. And this is done with the same. This is like a color palette for that. So yeah, that's 3D printing. You should all buy 3D printers. They're really cheap and they're cool. So let me just change this. Now, this whole Catapult thing started in 2012 when I got that crappy printer. And this is the first one I ever designed. You would like push it down, it would shoot little square calibration cubes. It had a little latch at the back that you could press and it would fire. And it got really popular on Thingiverse. It's, I think, one of the highest downloaded ones on Thingiverse, which is the site that you download 3D models for your printer for. But I always wanted to make a motorized one, because overcomplicating things is really what I excel at. So we now have this, and this is the catapult I've built. I know you can't see it properly. My wife makes fun of me all the time, but I'll tell you what I tell her. It's not my catapult that's small, it's the room that's big. So I need 3 people to stand up quickly. Just stand up. 1, 2, 3. Okay, left. Tell me which one is the catapult.
Top right.
Black shirt?
Top right.
Black? Okay, trick question. They're all catapults. What we commonly consider as a catapult is actually a mangonel. That at the top right is a mangonel. Now, catapult is actually the category. So catapult is a dog, and a mangonel is a Rottweiler. So these are all catapults, and it's because the word comes from the Greek kata, which means down or against, and palein, which means to throw. So basically anything that throws something from one place to another is a catapult. There's lots of different varieties, but this is the one we normally think of as a catapult. It works by, if you look at the top right there, by taking rope and twisting it, and uses the torsion of that to sort of spin the arm back and throw the thing. This has many downsides, like if it rains, the rope it's not as springy, so they're fairly inconsistent. The whole frame is trying to crush itself. Think of it like you have these bars there, and the whole thing's twisting. So as you twist it, the whole frame is trying to crush itself in. So they have to be much stronger than you would like. They also are very affected by the square cube law, which means that as you make the projectile bigger, you need to make the force that throws that projectile much, much bigger, like exponentially bigger. And that made it impractical to use them for like taking out walls. If you've ever played Age of Empires, you've been lied to, because you can just shoot down walls with the mangonel in that, but that's not how it worked. Like, you're shooting rocks that are this big. They were much more popular for shooting across a DevConf crowd, because they would shoot horizontally, and even if it's small, if you get hit in the head by a rock, like, you're dead. So this is a Ballista, which looks like a big crossbow, but, well, I mean, it is a big crossbow. So these were very, very accurate, and these were the first kind of, like, what we consider today snipers. Historically, like data we've got written down, which must be true because it's on paper, these apparently could reach 650 meters. Modern reconstructions have got to 350 meters, but even that 350 meters is way further than a normal archer could shoot a little bow. So that's why we had those, and they would use them to take out individual people on top of castle walls. This is a trebuchet. So trebuchets have a lot of advantages, like they're a lot more consistent. It uses the force of gravity on the one side to fling the thing on the other side, the projectile. And because you don't have a rope that can age and stuff, gravity doesn't change. If it does, we would have other problems. So it's always going to throw it the same. But now, these generally go up and then they come down. So they're better at destroying castle walls, but still, like, even if you could destroy castle walls that you're attacking, like, this is going to be your new home. Like, you don't really want to break the whole thing. So when history books and stuff show that they were used to, or Lord of the Rings show that they were used to take down castles, that isn't super true. These are less affected by the square cube law. They can fairly linearly be scaled up, so make the projectile bigger, make the weight on the other side bigger, and you're good to go. But they did require a lot of wood, because as you made them bigger, obviously you need to make them taller and everything, and you couldn't just go down to like Builders Express and pick up some planks. So it was kind of hard to take these to battle. They weren't just used for war. This is actually a historical picture of the door at the bottom was broken, so the Mongolians are visiting their Bettys over the wall over there. And now, if someone has a photo near the camera near the back, can you just tweet me an image of this? I need to get the sweet Reddit karma from it. But I've been told I need to have memes because young people. If you take anything away from this talk, take away that if you ever go to war, you need to use a trebuchet. There are so many advantages of it and so few disadvantages that make it by far the most superior siege weapon. The reason I built a Mangonel-ish, is that it's at this scale, a Mangonel actually works better because we can use elastic bands, which are just incredibly overpowered compared to the weight of the thing you're shooting. But as you scale it up, a trebuchet is going to be how you take out the zombies. So now the next part was using simulation. Simulation is, like physics simulation, is where you take some designs, you put them onto a computer, and you make it work it out for you. So if you look there, there's a soccer ball, and it's sort of showing roughly where that soccer ball would bounce. And I wanted to use this to optimize this catapult. Now, there's a lot of free, a lot of paid. The problem I found with all of these is that there's a lot of limitations. They are not made to do what I wanted to do, which was run hundreds of thousands of simulations to test different variables. These are made to design a car that you think is good and then test out certain things. So even the super expensive, very complicated ones, I didn't find I could do what I wanted. So what I actually ended up with was Unity 3D. It's a game engine that happens to have a physics engine inside it called PhysX, made by NVIDIA. It is not perfect. It is made to work at runtime speeds, not, you know, a lot of these other things can take hours to calculate the simulation. This will all happen in real time, but it's fairly good. Like, I imagine if we got attacked by a race of balls, this is pretty much how it would go down. So then what I did next was I designed this thing, which was a little catapult that had 7 different settings. So if you see the little holes along the bottom and the holes along the top, you can adjust that to test 7 different angles. And I 3D printed that. That's not a photo, but it is what I 3D printed. I then put that same design into Unity and made this. Now, it looks a bit blockier, but all the dimensions and where the holes are and everything are exactly the same. And I made a simulation. So you'll see that flings itself forward. So I'm going to show you that in Unity to show you how that actually works. Now, you use a thing called springs. Has anyone ever used Unity before? Like most of you. Cool. So this is Unity. If I hit play here, it's gonna, there we go. It's gonna show you basically what I just showed you in the video, so I don't know why I had a video. But if I go here, this is that catapult. And you can see it's got its like arc of where the bullet went, or the projectile went. So now, if I just grab this, and I grab the spring pivot, I've set that this is where, this is the spring. And if I drag this up, it acts exactly like a spring. I can jiggle it around, and yeah, it's basically a spring. So that is what I'm using to replicate an elastic band. It's not exactly the same as an elastic band, but it's a lot closer than using the other ways of applying force to something. You can also do stuff like, if I just pause this, I can change the fulcrum point. So at the moment, it's rotating on that black dot. I can just drag this across here, and pause, go back here. And now, if I move this spring, you see it's now rotating on there. And those changes make massive differences to how far it goes, how fast it goes, and these were the kind of things that I wanted to test out. Now in Unity, just to show that the 3D engine, the physics engine works in 3D, you can very easily create like a plane. You got a plane. Just add a rigid body. Should probably read that. So I clicked rigid body 2D. With 3D, you click the one that doesn't say anything. It just says rigid body. So this is now a rigid body. You can set it to kinematic. If I create a cube now, 3D object, cube, place it above it, add a rigid body to that too. Just drag that up. If I hit play, that cube will fall. And that's a physics engine. So I tested out that simulation with the 7 different settings and doing it in real life. And this graph sort of graphs the differences. Now, I was super impressed by how close this actually is. There's a bit of discrepancy as it goes on. My best guess is that it was actually a bad design of the physical model where the elastic bands I was using, as we got further in the tests, like 4, 5, 6, 7, those elastic bands started rubbing more and more, adding outside influences. But regardless, this graph told me that the simulations are close enough to roughly achieve what I wanted to. So then I changed the simulation to, work automatically. And there's 3 different things that this simulation, 3 different variables that the simulation changes. So one is the force position, like where the force is attached to. Another is the angle of the force, so like where the elastic band is pulling from. And then the last one is stopping point. So like you'll see it's that white dot at the bottom. You probably can't see, but it's there, I promise. The arm flicks up and where it stops. If it hits it vertical like this at a 90-degree angle, the bullet will probably go really fast, but it'll drop, and you won't get as much distance. So 45 degree is probably better because you go up and you come down. So this, I ran, at the top right, you can see how many tests it is doing, but that's just for this video. To work out the actual values for this, I ran it like 100,000 times and left it doing its thing, and at the end, it spits out values. So I'm going to quickly go to Unity and just show you the 3 different things that we change here, those 3 different variables. So this is that one you were just watching a video of now. Now, the 3 things are, this is the stopper, so that would be, vertical, or you could stop it here and the arm would barely move up at all before hitting it. Then you get the spring pivot. So that's where the spring attaches to, and that's like the angle. So you might think that putting it directly up from the arm is good, but the problem is, as the arm goes up, once it's parallel to where the spring is, any movement past that, the spring is actually pulling it backwards. So that's not great. And then the last one is just where the spring is connected to on the arm, along there. Okay, so now we're going to get on to designing. So we've got a bunch of values that Unity spat out, and we need to put them into a design. So there's lots of CAD programs. At the top right is Google SketchUp. It's very popular. It's also trash. Never use it. At the bottom right is Tinkercad. It's very simple and a lot simpler than the program I'm going to show you. But if you just want to design a little thing or are kind of scared of getting into the stuff, it's a good place to start. You'll hit a limit very fast, but it's really cool for beginners and might give you the confidence to move on to a more complicated program. And then there's Fusion 360. It's made by Autodesk. It is free for education and possibly doing talks, I hope. It is really, really good. They do also have a paid version, and a lot of professionals use this over things like SolidWorks and whatever, because it is a great mix of being easy, being fast, and it's got this whole cloud thing, which, I mean, you guys know what the cloud is. It means you can hit save and something happens somewhere. So it's cool, I'm sure. But I took that and I made this. There is no reason for this video. I just really liked making a little video that looked like a Surface commercial. It also has animation tools, so you can click a few buttons and hit explode, and it kind of explodes your whole model. But this sort of shows what I was saying about how overcomplicating things is really good, because imagine if this just had 3 parts. It would just look lame. So make sure you overcomplicate things is, I guess, what you can take away from the talk. Now, I'm going to show you some Fusion 360. Have any of you used any CAD or CAM software before, by the way? Cool. Like 3 as well. So this program, it might look daunting because there are a lot of buttons, but like Azure has more buttons. Now, this program works on something called parametric design. And what that means is that you can do a whole bunch of stuff, and it makes a history of the things you have done. If you want to go back to the beginning and you want to say like, oh, actually, I'm meant to make this part angled like that, you can literally drag back time, like Doctor Who, and it'll go back to that first step. You can edit it, and then you can drag the timeline forward, and it replays every step that you've done after that back onto it. So if you design things really well, it can mean that if you make a mistake or want to change the design of something because the parts that you were using, like you want to use a bigger screw or whatever, it literally just all flows on top of it and is just really, really fast to use. So I'm going to show you quickly creating a little catapult. So everything starts as a sketch. I click Create Sketch. It's now asking me what plane to do it on, so I'll just do it on the side plane because we're going to design the catapult from the side. Now, I'm going to create a rectangle. Just going to make it 10 mils high and 100 across. Can zoom in there. Then we want to make the arm that goes up, so I'm just going to create a line by pressing L. Just going to go 100 up. And then I'll create another line down to the bottom. Now, this will create a solid triangle-ish thing. But we don't need that much plastic. We don't want to waste plastic, and also you don't need it that strong. So what we can do is we can make a hole in the middle by just shift-selecting each of the lines, pressing O for offset, and dragging it in. So I can drag it there, hit OK, and now you see when I move my mouse over here, that's one object and this is one object. So I'm going to stop sketch, rotate around, that's the sketch we made. Then you can hit extrude. Now extrude is taking a flat thing, making it a fat thing. Like, think of it as McDonald's button. So now you can select all the parts you want to extrude. And I'm going to drag it out, and you can choose how thick you want to make it. I'm just going to go 10 mils. And that's our one arm. Now I want to have a base piece that goes across and connects to the other arm as well. So I can open up my sketches. See, it's automatically hidden the sketch that I used because it doesn't think I need it anymore. You can just turn that on, and you can see our sketch we originally created there. Just extrude again, drag this. I want to go minus 20 this time, because I want to go 10 millimeters further. By default, if you're extruding through something, it'll try cut it. That's why it's red. You can just change the operation to join, and hit OK. So there's our base piece. Now I am going to create an exact copy of that on the left side. So to do that, you create a mirror of it. So create mirror. Then by default, it's got faces. A face is like a flat thing. So that is a face there. That's a face there. That's lots of faces there. Now, you can change that to body, and you'll be able to select the whole object. So you can select there, and then you can choose the mirror plane. I want to copy it exactly around itself, so I'm just going to select this plane on the side here. And in light gray, it shows us the preview, so that's perfect. Can hit OK. And that is a very simple catapult. Now, if I wanted to smooth out the sharp edges on top, you can do a thing called fillet. It's different to a steak, but it does do that. So it smooths it out. It looks really nice. The problem is I'm going to have to do 2 of these. I would need to do it to both of these points. And then you're just creating more history. And if you want to change one, you've got to change both. It's a mission. What you can do instead is you see this history line at the bottom. I can drag this back to before I actually mirrored it. Go to the fillet. Make the fillet that I want. I'll maybe add another one to make this inside triangle prettier. Just drag that out so it looks good. Cool. Hits OK, and now I can drag this forward in time, and you'll see that the thing that copied automatically has those fillets. So that's a very simple example, but it works for hundreds of steps. This is the actual catapult that I designed, this thing over here. Now, if you look at the bottom, this history got very complicated. And these are all actually groups which have hundreds of things. So if I open that up, these are all individual commands, if you can see at the bottom, that I did. And if you want to go back in history to like see how things were made, you just drag this little bar to the left. And each time you let go, more and more stuff will change. So theoretically, I could go back to the first sketch I ever made, and I could change the size of, let's say, the bearings that I'm using. Click Finish, it'll go all the way to the end, and everything will resize around those new bearings. So that is Fusion. It's really cool. Don't be scared of it. There's lots of videos on YouTube about it. Yeah, it's really good. So this is a video to show how this whole mechanism works. Now, I'm going to let you watch it just once, because it's very exciting. Now, one thing that isn't shown here is that arm that comes down, it's actually pulled by a belt. The belt isn't there because it's a bitch to animate. So if I go back to the beginning here, first, this little latch over there, the latch opens up so the arm can come down. Hello, Pop? Whoa. Okay. Then the arm comes down and gets pulled by that belt. The arm comes down, and it pushes that other blue little latch, which allows the bullet to fall in. At the same time, the other latch on the side locks that arm into place, and then we unwind the belt. So this whole thing is driven by a belt that pulls down the arm. But once you've pulled it down, it's like wrapped around the motor. And if you were to let go that arm, it would have to unwind the motor, which is adding a ton of friction and wouldn't work. And so we need a better way. So what I've done instead is you pull the whole arm down, then you latch it with the little servo, and then the whole motor unwinds, and it makes the whole belt slack, and then it fires. Once we finish designing, we can 3D print it. So this is an, oh, by the way, epileptic warning if anyone is sensitive. This is a pretty bad time lapse of the 3D print of this. It's a different color because I made many of them, which I'll show you in a bit. But yeah, so you 3D print it. Now, 3D printing is a very iterative process. You need to get used to designing something and then changing it multiple times, because unless you're amazing, which I'm sure you all are, you won't get the thing right first time. And this has a lot of moving parts, like literally moving parts. And printing, 3D printing, your sizes aren't always perfect. So you might make something 10 mils, stick a 10 mil bearing in, and it doesn't actually fit. So what I do instead is I design and print individual mechanisms first and get each one of them right and then work on the bigger product. To make this, I went through weeks of printing probably 2 kgs of plastic, which is like 400 rand of plastic, and did a lot more than that, but those are the ones I had in a packet, and that's a puppy for scale. So now that we've got the frame, we need the hardware. And on the left, you can see an ESP12E motor shield. So if you just get a little Arduino and you try to run a motor directly off the pins, or even a servo off the pins, you'll probably burn out the pins. They can't output enough power to run those motors. So instead, you need a motor driver. It's got a fancy chip that can drive bigger motors, and it won't affect the Arduino, but it's still driven by the Arduino, and it's got cool things like you can change a pin and set that motor to reverse, like we do when we unwind the belt. Then we have the ESP8266, and the specific revision of it is the 12E, and that's like a little dev board. If you were at my talk last year, I used a smaller one called a WeMOS. This is exactly the same, just bigger for no apparent reason. Then we have a 6-volt geared DC motor. This requires quite a lot of power to push down this arm. Like I am showing off here. I can do this easily, but the motor struggles. Now, what I've done, instead of getting a really, really high-powered motor, is get a pretty bad motor, but on top of it, it comes with a whole metal gear thing. It's like a reduction thing where for every 1 turn, or every 10 turns of the motor, it'll only spin the other side 1 time. And that makes it much more powerful. It also makes it slower. But you can fix that by doing things like over-voltaging it. So it says it's a 6-volt motor. You can throw 30 volts at it. You might burn it, so I'm not going to do it on stage. Saw what happened the last time. I tried something earlier. But yeah, so those are really nice. Then we have an end stop, same thing as 3D printers. You need to, a DC motor has no idea where it is. It can spin for half an hour. It won't know whether it's pulled the arm to here or here. So you have a thing like an end stop. Now, it's a little clicky thing. When something touches it, it shorts 2 wires. So I'm using a chair for, as the arm gets down to the right position, it clicks that, and we know the arm is in the right position. Then we have a servo. That's just to latch and unlatch the arm. Okay, so now we need to control it, because everything needs an app. It really doesn't, but it's cool to add it. So I made an Arduino app. Now, last year, when I made the potato cannon, I showed a way to use Unity, use an HTTP client, connect to it, send commands over, and and just control it like this. This year, I had a lot more time, so I instead did something that was much simpler. So that's Virtuino. You can drag things in, like drag little buttons and create a whole app. You can even export an APK. Blink is similar, but it's a lot more expensive, and it has to be cloud-based, so you can't do it directly connecting here. So now we get onto code. You think I have 5 minutes left?
We've got a bit thing, so it starts at 22. We started 10 minutes late.
Okay, so the Arduino code, I'm going to have this all on my blog, and I'm not here to teach you Arduino. I'm just here to show you generally what's possible. So I'm not going to go through all of this code, but one thing I will show you is really cool with these ESP8266s. At the top here, so I've included the ESP8266 library, and that allows us to do Wi-Fi things. So this will create its own hotspot, and that's so that people don't connect. That's where you set like the SSID and the password, and then you would think that creating a hotspot is really complicated, but with this, it is these 2 lines of code there. And magically, that turns into a hotspot. You can have a web server on it. You shouldn't, but you can. And the rest of the code basically just makes the motor spin forward, back. It's all very commented. It will be on my blog if you want to check that out. So now, some people have asked me, why do you need to make this thing automated? Now, automation and making the whole thing 3D printed and everything, the real point of it is just because it's cool. Also, it has Wi-Fi, and anything with Wi-Fi is cool. It also has an app, so it fits right in with 2017, and it's repeatable. So this is not actually a looping video. This is one long video. It goes for about an hour of my friend just catching it over and over again. And yeah, we shot one. He put his hand where it went, and then he just held his hand there, and it goes into exactly the same position, because computers are not fallible, and humans are. What's really cool about this whole setup is that you can all build it with stuff you got lying around at home, as long as you live at an electronics store. So now, I'm going to go to my camera here. It's this camera. And this is our catapult. This is not our catapult. Thank you. So this is the catapult. And I'm just going to quickly show you like the loading mechanism. Do we have time? Maybe not. So I'm going to show you firing it. But to do that, we need to load the app. So I'm going to open this little app called Skirkopy, which allows me to show my Android screen on a computer. Okay, so this is my phone. I'm going to turn the catapult on. It'll create a Wi-Fi network. Don't read my messages. So here you can see there's a catapult Wi-Fi. It's going to connect to that. Cool. So I'm connected to that. I can then go to Arduino, where I've made this little app to control it. Let's put that to the right side, the camera on the left side. And if I hit this big red button, that's actually silver, it will not shoot. Oh, so this is something I wanted to show you. At the bottom left, there's a little network button. You choose which catapult you want to connect to, and then you hit connect at the top right. Now, if I hit this big silver button, there you go. So it pulls the arm down. It'll load a bulletin. It unwinds the belt. And you can also see on the right side, it's got a little gauge that shows you when it'll shoot. And that'll just carry on shooting forever until the battery dies or you run out of bullets. But yeah, that's the catapult. I need to know exactly how many minutes. Okay. Really quickly, we need 5 people up here. We're going to give away, we'll ship them to you. We're going to give away 5 of these things. So first 5 people to the stairs. Candace, can you? Whoa, 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 whoa. Calm down, calm down. 1, 2, 3, 4, 5. Okay, keep full. Okay, so you're going to catch a marshmallow in your mouth. If you catch a marshmallow in your mouth, you get one of the devices. So watch this final bullet, watch where it goes, and then you have to stand in the way and catch it with your mouth. It's very hygienic. Okay, so come on. Quickly. 5, 4, 3, 2. Okay, next person, come. 3, 2, 1. Next person. You can tell this was made for accuracy, but with plastic bullets, not marshmallows. Oh! Next person. 4, 3, 2. Oh! Okay, next person. Marshmallow. 4, 3, 2. Okay, don't worry. We're going to give them to all of you. Please go to Candace and take a photo of your name badge. So that's sponsored by Dev User Group. If you want details, they run in 3 different cities. You can speak to Candace, blonde lady, afterwards about that. Guys, thank you so much. So if you have any questions, I don't think we have time now, but you can tweet me, or I'm going to go to the unpanel room, and you can come chat to me. Also, there's my Twitter and my blog. It'll be up there soon. And please also go rate all of the talks. It's devconf.co.za/rate, and I hope you all enjoyed it. Thank you.